Hello. So I will talk about non-perturbative standard model field configurations as liquid crystal-like topological excitations. So in standard model, we usually work in the perturbative approximations with Feynman diagrams, which represent in abstract way some complicated scenarios. So it is valid like apple plus apple equals two apples. However, we can still ask about deeper so-called non-perturbative picture. What hides behind these apples or Feynman diagrams? For example, electron can be represented as perfect point in Feynman diagrams. However, there are fields, electromagnetic fields. So in this non-perturbative picture, electron needs at least this electric field, 1 over distance square. Moreover, this field should have quantization. We can have elementary charge, but not half of it, for example. So we start with reparation of this lack of charge quantization. So let's think about the Gauss law. So here's the standard Gauss law that electric charge inside a region can be found by integrating electric charge over the surface of this region. However, it returns a real charge being a real number. So, but we would like to repair it to have quantized charge. And it can be done by using so-called Gauss-Bonnet theorem, also like Gauss, but using this curvature of some deeper n field here as electric field. And so this way, we have this Gauss-Bonnet theorem. We again integrate this curvature Jacobian of this curvature. And this way, we get the number of wrapping of this field around the sphere, which has to be integer. So interpreting curvature of a deeper field as electric field, we would get Gauss law with built-in charge quantization as we observe in nature. So here is the basic Lagrangian I will consider. So includes further particles and interactions. So like in electromagnetics or in Skyrmion models, we have this F mini term, but now with 4 indexes. So now this F is interpreted as curvature of some deeper field to have this built-in charge quantization, like here. And full curvature has to use 4 indexes. So this is so-called dual formulation. So in standard formulation, we would get magnetic monopoles this way. But using dual formulation, they are electric instead. So thanks to that, we have only electric monopoles, charges, not magnetic monopoles in this view. Yes, so there is also this Higgs-like potential, which is required for regularization of singularities like charges. So here we literally fix shape of this molecule-like. So here are this liquid crystal-like structure I will use, and the shape which is fixed, enforced, preferred by this by the Higgs potential. So here is the shape, the final shape of the molecule I will use, preferred. But in the center of singularity, like here, it has to be regularized to get finite energy. So I will start with this one-dimensional situation, then go to this liquid crystal-like situation, and try to convince you that there is very nice agreement with the particle physics. Okay, so let's start with electron. So while in Feynman diagram, it is a perfect point. It has this electric charge. It has to be quantized. Magnetic dipole moment. It's a kind of a gyroscope. Has angular momentum. Also have a clock called Zitterbewegung, the Broglie clock. So this clock is required by relativistic quantum mechanics that having Schrödinger-like equation, this energy has to be mc square for relativistic theories. So this way, resting particle already should have some oscillations. Yeah. So for electron, this is Zitterbewegung. For a neutrino, these are oscillations, more sophisticated evolution. So I also talk about. And the clock for electron also was observed experimentally. So there is this very nice article that they have used fast electron, 81 MeV electrons. Thanks of that, the distance between ticks of the clock agree with lattice of some silicon crystal. So they get the resonance between the clock and the spatial lattice getting increased absorption. Yeah, this field configuration, non-perturbative picture is quite complicated. You'd like to understand it. What hides behind this abstract point in Feynman diagram? So here is the picture I will use. So we have the hedgehog of the long axis here of this liquid crystal-like field. So hedgehog is the quantized uh, topological charge, which we interpret as electric charge. Thanks to dual formulation, they are not magnetic monopoles, but electric monopoles. So elementary charge. And we can see that there is also this twist of the field is recognized. So it's crucial for many from many the directions. For example, for angular momentum, we should recognize this twist. And for this clock, we can see that this evolution could be the twisting of this field. So I also mentioned the mechanism which should propel this clock for elastic particles, so technically making them time crystals. And having this evolution, this constant twist of the field, we got angular momentum, clock, but also the magnetic dipole moment. This rotation will be required for angular momentum. Yeah. So finally, the non-perturbative view of electron will be this kind of evolution. So besides, there are many more particles. For example, neutrino was always thought as being perfect point. However, recently there were this experiment showing that neutrino is like 1,000 times larger than the nucleus, to 6,2 picometers. By looking at electron capture of this beryllium-7, so it captures electron, transforms into lithium-7, and produces neutrino. And here are the momentum distribution of this neutrino. They measure through recoil, and from this peak, this singular peak from Heisenberg principle, they get the size in space kind of wave packet as 6,2 picometers. Yes, so neutrino is quite complicated. So why it is in perturbative approximation, it is imagined as a perfect point. In fact, it's quite complicated. It should be field configuration of a very large potential size. So we will also discuss it. And moreover, it has in three types. It's much more stable than electromagnetic photons. It can go through Earth. It have these oscillations as a resting configuration. So we will talk about it, how to get it also. Okay, so let's start with this simple one-dimensional setting, so-called Sine-Gordon model, which can be realized by this simple lattice of pendula. So this pendula has this potential, gravitational potential, which prefers the pendula to be down. However, here we can see that we go from one down, the vacuum of this field, by 2 pi to another vacuum, also down, but with non-trivial constraint, the boundary conditions requiring this kind of configuration, which should minimize energy. Yes, and this configuration hides some energy, and to destroy it, we have to meet it with a anti-kink, anti-particle. So it is kind of massive particle example. So literally, it has to have lower velocity. When we speed it up, this is Lorentz invariant Lagrangian. There is Lorentz contraction. So here is a traveling kink. It is narrower, we can see. And if we meet it with antiparticle, we can get the annihilation and produce the energy which is now imprisoned here will be released as photons, as non topological waves. Okay, so this was one-dimensional situation. For higher dimension, the liquid crystals seem very promising. For example, there is this analogy between electromagnetics and hydrodynamics that, so especially for superfluid without viscosity, the formulas are very similar, with main difference is that here is speed of light, here is speed of sound. So there are many articles. So the question is how to add the charges to this kind of electromagnetic-like. So why there are these nearly singular charges which have Coulomb-like interactions. And to get this charge quantization, we can do it by topology. For example, it is observed by for liquid crystals in many articles, like shown here. So, for example, they create this configuration of charge anti-charge, which are quantized by topology, as we will use, and look at the distance, and we can they fit the type of interaction, getting, for example, Coulomb-like interaction. Yes, so we can get electromagnetism like with Coulomb-like interaction effective for topological charges which are quantized. Okay, so there are many types of topological defects. So here are the basic ones. So for example, they can be domain walls. However, for liquid crystals like here, field like this, molecule like this, and this is the same. So it can avoid domains. So that's an open question. We can add it, we can avoid it. So it is not necessary. We need these two type of topological defects. So one is this point-like defects. In dual formulation, as mentioned, we interpret not as magnetic monopole, but as electric monopole. So this is our charge. But we also need the vortices. Yes, it is hard to avoid them, and there are many arguments. They are also crucial in fundamental physics. And in microscopic physics, they are often interpreted as so-called gluon flux tubes, quark strings, connected quark-antiquark pair. So now the question is how to get the quarks, for example. So quarks have fractional charges. So can we get fractional charges? And yes, so having this kind of view on quark strings, so we need quarks as fractional charge excitations of this quark string. So by inward outward rotation, we can see that here we can perform this. If performing this inward by pi rotation, we would get elementary charge as topological. But we could also make, let's say, p-third, one-third, so to get quark-like excitation. Yes, so here is very low energy. Here is this by pi-third rotation, and now we see there is conflict. So we can do it, however, this conflict, there is kind of singularity inside. So if our Gauss law cuts this conflict, it doesn't have to be exactly integer. So the Gauss law that cannot cut singularities. Here it would cut singularity. And this conflict in QCD is known to have asymptotically linear energy. Yes, so this is one GeV per femtometer. This energy of this conflict asymptotically, and for low distances, this is Coulomb. Yeah, so as you can see here, it should be Coulomb, then asymptotically it should be linear, as in QCD. So it agrees well with QCD quark strings. So then, how to get Faber particles? And there seems to be very nice way to get Faber particles, because there is so-called string hadronization. This is a basic way to model, for example, LHC collisions that they smash these two protons or nuclei, and they get many particles, and they model it through this creation of this string, this quark string, like this structure, and look. So the question from topological perspective is what topological vortex like here could decay into. Yeah, so we need to find the correspondence between what topology allows it to decay into and what they observe in LHC collisions. And this topology should suggest us which particle has what non-perturbative structure. So we'll go this way, and I think it's very promising. Okay, so the question is, are these one-dimensional structures physical? Yeah, so there are some maybe more science fiction ways, cosmic strings, but generally, if you have quantum mechanics and the quantum phase makes it should have 2 pi or its multiplicity going over a loop. So through such loops with non-trivial change of total quantum phase, there have to go topological vortex. So quantum mechanics alone seems to require some one-dimensional topological vortices. And there are many arguments. So I think, for example, there are these halonuclei. There is a core, and there are these one or two neutrons or protons large distance, for milliseconds or relatively stable in distance many times larger than of nuclear force. So the question, what binds them? So maybe this topological vortex would be crucial here, yes, to get this binding. And for example, in Sun's corona, they observed these shining lines. They call it magnetic flux tubes. So the question is what makes them stable, and they don't really know, but they again suspect that they might be topological. Like I hear this from a book quote. There are many arguments that there should be and there could be topological 1D structures in this microscopic scale, and for example, as these quark strings connecting quark-antiquark may be inside for structure of nuclei. Okay, so these topological vortices, one-dimensional structure, are well known in superfluid superconductors, as called as fluxons. So we can calculate the magnetic field by integrating this by integration. So getting quantization of magnetic field this way. And now going to QCD, it seems very similar. So again, we need this quark string and its excitation of fractional charges for quarks, which asymptotically, which Coulomb interaction for very short distance and going to linear for very long. And this is indeed true here. Yeah, so locally we have Coulomb-like interaction. Then asymptotically we have this linear structure with fixed shape and some energy density, which would be approximately 1 GeV per femtometer. Okay, so also I mentioned this halo nuclei. So there are, for example, lithium-11. There is the core and two neutrons, but there is also a proton halo. So we have positive core and positive 1 or 2 protons, for example, for boron 8, neon 17, and many others. And it's for milliseconds. So we have, for example, strong repulsion for proton. For the nuclear force, we can see that it has minimum below 1 femtometer, but somehow these single nucleons hold very stable way for milliseconds in many times larger distance than its minimum of nuclear force. So the question is, what holds them? So I think that the only reasonable type of answer could be including the topological vortices. Yes, that literally there is some topological vortex and allows to bind this halo nuclei. I've talked about it with many persons and nobody have. So there are effective models again. You can put by hand this kind of interaction, but what is non-perturbative view? What's happening there from field perspective? So topological vortices, I think, could be the only type of answer if you try to search for concrete mechanisms. Okay, so maybe some two more philosophical slides. So we can think about coupled oscillators from classical perspective, but you can also go to these normal modes and you get kind of quantum evolution. Then going to crystals, we get again classical, but we can also go to phonons, which in QFT, quantum field theory, becomes quasi-particles. So the big question is, what about the continuous limit? So from one side, we get the atoms. And then turns out that for example, for the bouncing droplet I mentioned, they get this kind of quantization orbitals. So we get the droplet which is bouncing, and it creates the coupled waves. And the quantization condition becomes that this coupled wave has to become standing wave, like in stationary Schrödinger equation. Yeah, so we can get also this resonance condition as in Schrödinger. In classical wave particle duality situation. Then finally we get the situation with varying number of particles. So we are used to Feynman diagrams in the standard model, but we should also be able to ask about the fields which are hidden in given Feynman diagram, or from the other perspective, if you have some scenario in fields, how to describe it effectively using Feynman diagrams. Yeah, so this is a non-perturbative view. This is perturbative view. Yeah, so Okay, so as I mentioned about this orbit quantization, so there are lots of articles about this the similarity between topological defects like fluxons and the quantum-like properties, and bouncing droplets, that there is a droplet and there is shaking surface, and that there are created coupled waves. So for example, they get this double slit statistics that the droplet goes one path, but its couplet pilot wave comes all the paths and controls the trajectory. They get the orbital quantization. This couplet wave has to become standing wave, as in stationary Schrödinger equation. Not only of two quantum numbers, both this n, but also angular momentum. So getting this kind of quantized orbits. Again, the standing wave, the coupled wave has to become standing wave. Okay, so now I got the main part that we have this. So we would like to have these models of particles as liquid crystal-like configurations. Yes, so we start with this reparation of these two problems of electromagnetism. One, that the Gauss law has to be quantized. So we use this instead of the Gauss law, we use this topological version called Gauss-Bonnet theorem. Second problem is that the charge has infinite energy, so we can repair it by this mentioned Higgs potential. For example, like here, so we have this topological hedgehog here or here, and so there will be problem in the center, because if we would have to use unitary vectors, it would be discontinuous in the center, would have infinite energy. So what we can see that thanks to Higgs potential, these unitary vectors can go to zero vector, to no longer have to this discontinuity. We can get a regularization to finite energy thanks to the Higgs flux potential. Yeah, so here is for charge 1, here is for 1/2. If you go around, the number of rotation of the field is 1/2. So we can also get the kind of spin 1/2 configurations here. So then we get this topological charge as quantized electric charge. Then we can, for example, get you have three different axes. It's called biaxial nematic. We can get hedgehog of the three axes, so kind of three leptons. Additionally, if we align if we perform hedgehog with one axis and try to align the second axis on the surface, we cannot do it, and there appear these additional conflicts. So there are no naked charges here. So as for leptons, there also need this magnetic dipole moment. So there is this called Hale-Bohr theorem, which allows to explain why there are no naked charges. They also need some additional singularity of magnetic dipole moment. Finally, here you have three different axes. We can go to 4 dimensions, so then add boost to the rotations. So now our three different axes, we get fourth axis, also very long axis in the temporal direction. Yes, and it is much more difficult from energy perspective to rotate this fourth axis, this temporal axis. We will get the second set of Maxwell equations, but now for gravity-electromagnetic approximation of general relativity. Yeah, so we get also gravity this way by going from 3-dimensional to 4-dimensional situation. Okay, so now let's start with these 2-dimensional topological defects. So this topological charge, the number of field rotation, if you make a loop around, so here is +1, here is -1, here is +2, here is 1/2. If you go around, the field rotates by 1/2 of the full rotation. So we can also get 1/2 thanks to the symmetry that this field and this field is the same. As for this issue that there are no domains. So that's, I think, open question if there are domains in fundamental physics. So sure, we can get them in ferromagnets, but are there some cosmic domains? I'm not certain. So we can add them, we can avoid them. Okay, so if you can 1/2, in 2 dimension, it resembles spin. Yes, so we can also think about why G factor is 2, because G factor connects angular momentum and magnetic dipole moment. So this 1/2 is structural, but the dynamics. I think that G times 1/2 should be approximately 1 because this 1/2 is only structural. Well, we should use dynamical, so evolution, field evolution instead. Okay, so this 1/2 is in agreement with quantum rotation operator that spinous particle that if you rotate it by theta angle, the phase rotates by s times theta. So this is also here. So finally, going to 3D, we would get this, for example, this Hedgehog-like configuration. So here are two-dimensional. I interpret as spin. So there are many arguments also because it's magnetic. And for 3D, we interpret it as electric charge. And get the Coulomb interaction. Yes, that getting two charges opposite together reduces energy, like here. And there is also this clock. Finally, there can be also this field phase rotation. Okay, so regarding this charge quantization as a topological, so here is the analogy. From one side we have electromagnetism, the Gauss law, and there is topological version. It's called the Gauss-Bonnet theorem. Like in Gauss law, but integrating curvature of some field, we get integer number of some Windic number of sphere, for example. So as in Faber's approach, we will use here is some n field, some deeper n field. We define its connection, so local rotation as gamma. Then we get the curvature as cross product of two gammas. Then we use electromagnetic Lagrangian for this f as f tensor, standard f tensor as curvature to make the Gauss law count topological charge. However, in fact, the interpretation is that we use dual F as R. Dual means that we replace electric and magnetic field to get quantized electric charges, not magnetic monopoles. Yeah, so if you don't do dual, you would get magnetic monopoles, which more likely do not exist. But I know this is a discussion, but we don't observe them. So this way we can avoid the problem of requirement of magnetic monopoles, because we have only electric monopoles in this dual formulation, also using quantum chromodynamics. Okay, so let's think about the Coulomb interaction. So here is approximate calculation of the Coulomb interaction. So we get two topological charges in various distances. Here are the same positive charge. Here are positive, negative, opposite charges. So the color represents the energy density. And we can now integrate the Hamiltonian, being this sum of squared curvature, as mentioned. Yeah? So as electromagnetism, but with curvature interpreted as F tensor. And we calculate integrating this energy density Hamiltonian. We get effective, literally, we get the points which agree with 1/, distance Coulomb potential. Yeah, so working with such topological defects, effectively we get Coulomb-like interaction for this kind of configurations. Also having Lorentz invariance, this way we get full electromagnetism. So this calculation has two approximations. So one is guessing this configuration. Second is there is this cutoff to remove the singularity in the centers of charges. So to remove this singularity, as mentioned, we need to use the Higgs-like potential. Yeah, so we get unitary vectors. However, they can be deformed to the let's say zero vector in the center to avoid the singularity. So thanks to the Higgs-like potential. So from energy perspective, so here is this radial field which will go to infinity without the regularization. But thanks to regularization, there appears these two different fields. So one is this potential field, and the second is also the tangential field, which derivative for change of length of this vector. Yes, there is also. It also appears. So there is no part construction of electron. So here we don't. Electron is not It does not have any partons. It's still point-like particle. However, it is not perfect charge electric field. So if we assume perfect point electric charge, then the energy of electric field alone would be infinity. So it would be very bad. So we need to regularize it. And here, literally, we deform the electromagnetic field in the center of electric charge to avoid the singularity. Yes. So if we do it, there is some deformation of Coulomb interaction for very low distance. And Matthew Faber team has calculated it. For example, getting this kind of points. So versus the Coulomb is the blue line, and the red are the calculated numerically. So we can see that Coulomb interaction becomes slightly stronger for very short distances. And it is turns out it is in agreement with so-called running coupling effect. That for very high energy, the alpha controlling Coulomb interaction is deformed into stronger, like here. So we can see that this effect of deformation of perfect point charge, which is required to not to get to infinite energy for this singularity, but it should integrate to the mass of electron, the 511 keV, its energy density. To repair this singularity, we get deformation which are in agreement with the running coupling. So this is alternative view of explanation of this running coupling effect, but just repairing singularities to get the finite energy. So the question is, how does it compare with the belief that electron is perfect point? So it turns out, if you look at the evidence for this belief that electron is perfect point, so one is based on G factor. So it was proposed by Bedelmert, who has calculated the G factor very precisely in 1988, I think. So here is the plot he has used. So he has assumed that electron as being made of three partons. So once again, we are not assuming any parton structure for electron, just repair the singularity. But he has assumed that electron is being made of three partons and compared it with proton being made of three quarks and triton being made of three nucleons. So here is G factor -2, here is the radius. So we can see that this is not a straight line. So if he would use a straight line, he would get negative radius for electrons. So it makes no sense. So he has extrapolated with parabola from 2 points. Yeah, so we cannot do it. So you can do any value if you extrapolate from 2 points with parabola. So this reasoning makes no sense, but it is very common argument based on G factor. So, but I think it's completely useless. So let's think about better uh, evaluation of size, experimental evaluation size. So one could be the running coupling, as mentioned, that literally. So here is Manfred Faber, and here are the some two textbook view on the running coupling. So turns out that different textbook lead to different predictions, and Manfred was kind of in the middle, but still there are needed some correction. But generally, the qualitative behavior is right. So another experimental view is the electron-positron cross-section. Yeah, so here is the plot for very high energy in GeV. So here is like 100 GeV here. So what we can see in log plot, that there is basically a line plus resonances believed to be correspond to particles. But these are extremely high energies. Why we are interested in size of a resting electron? So to remove Lorentz contraction and different effects, we should extrapolate this line to the resting particles. If we do it, we get like 100 millibarns corresponding to like 2 femtometer size. So again, similar signs as required not to exceed a mass of electron with its electric field alone. Yeah, so again, it's in agreement with the size. So it sounds that they see this deformation required to avoid infinite energy by perfect point charge. Okay, so regarding similar models, so there are these Kirmian models I have mentioned, and they use one of terms they are using is practically the same I'm using. So they're also curvature square. So this is very similar, and they get these models of nuclei like here, and they are very popular. However, there are some differences. So the main difference between our view is one that they interpret topological charge as baryon number. Instead, we interpret it with matrix Faber as electric charge. Yeah, so if I interpret it as baryon number, then this number cannot be validated. However, there are at least two processes which are believed to validate this baryon number conservation. One is baryogenesis, that was created more baryons than antibaryons after Big Bang. Second is Hawking radiation, that we can take baryons, build a black hole, and it will evaporate, radiating massless radiation, so no baryons. Yeah, so to destroy baryons. So there are many problems. There is no Gauss law for baryon number. We don't believe there. I don't think anybody believes there is Gauss law for baryon number. So maybe the better interpretation would be for electric charge. So electric charge, I think everybody believes is conserved. So if you can do it for one property, I think it's better to use it for electric charge, not baryon number. So this is one difference interpretation, but to get a long-range interaction, Coulomb interaction, we need also to change the potential. So Feynman model use usually this potential with single minimum, while as mentioned many times, we need Higgs-like potential. Yeah, so that there is preferred these unitary vectors, and the interaction of the field rotations give us electromagnetic interaction, for example, long-range Coulomb interaction. So yes, we literally interpret curvature as yeah, so it's very similar. But if you're having this Higgs-like potential, so dynamics of rotation literally brings electromagnetism plus quantum mechanics plus gravity. Okay, so yes, so as mentioned, so we have dynamics of this kind of object. So this molecule-like object, elongated, its dynamics of its tilts will lead to electromagnetism. Yeah, so the hedgehog of the long axis will be the quantized electric charge. However, we also need to recognize twist of this object. Otherwise, for example, angular momentum would be not conserved. Yeah, so we could get the rotation, but this field will not see the twist. But we can make it that energy contribution of this twist is much lower than of the tilts. Yeah, so we literally do it. So now the rotations, the final rotations of this object. So here is the spatial rotation. So we have the tilts, the high energy tilts, plus a low energy twist, the blue line, and finally for Lorentz invariance we also need the boosts. Yeah, so also there are also boosts here, which have different sign here. So finally, the blue contribution, the quantum phase, for example, is required in Lagrangian of QED, quantum electrodynamics, there is both electromagnetism term, but also low energy, this quantum phase. So there is derivative of the quantum phase. Yeah, so there is very large, relatively large, this contribution of electromagnetism, but also this h bar c, so very small contribution, including this evolution of phase. And here we can get it from this twist evolution. We can include lower energy for that, because our field is this kind of field with this diagonal having a shape, this long axis and short axis. So rotation will twisting brings much lower energy contribution. Oh, it should be reversed. Okay, so it should be blue, should be green. Derivatives. Okay. Okay, so and now finally there is also the time axis, which has a tiny contribution leading to second set of Maxwell equation for the gravity. So there is this gravity electromagnetism, like so to make Coulomb law itself is not a Lorentz invariant. To make Coulomb Lorentz invariant, there is added magnetism, Maxwell equation. So we can do the same for Newton to make gravity Lorentz invariant, but adding gravito-magnetic field. Yes, the same as for magnetism, but gravitational version. And so this is required to make gravity Lorentz invariant. It is also the kind of the first correction from general relativity. And this correction was directly tested by gravity probe B. Yeah, so we can say that in fact gravity probe B tested gravity electromagnetism. So this is the first correction we need to include. So besides, there are also interactions between these electromagnetism and gravity in these kind of approaches. They're coupled. So, for example, uh, electromagnetic interaction will be slowed down in a gravitational field. What allows for both the light bending from Fermat principle, but also time dilation because chemistry and everything is based on electromagnetic propagation. So it also leads to time dilation. This interaction between electromagnetism and gravity. So there are also these deformations. I mentioned that the shape of the vector is usually unitary, but can deform. And if we think about this deformation, it resembles the Yang-Mills model, so the strong interaction. So this deformation, I think, corresponds to strong interaction and weak interaction to dynamics of the vortices. If you ask about non-perturbative, what they mean, I think it seems it's dynamics of the topological vortices. Okay, so here is another view. So we need this for Coulomb interaction for electromagnetism. We need this S2 vacuum that we have these unitary vectors and they can make a sphere. But for quantum mechanics, we need S1 vacuum. So we have this phase which rotates some in one dimension. And now we combine both, unifying kind of electromagnetism and quantum mechanics, like here, that we have the long axis and the twist. And so we can see it as kind of extended quantum phase, which combines both the quantum phase and this phase required for electric charge quantization. So we get Maxwell for this basic phase, plus close to Klein-Gordon for this quantum phase. So finally, for example, the momentum operator has both the derivative, but also a field. But in this view, the a field is already some derivative. Yeah. So for example, you can see it in the quantum phase over a closed surface using this kind of standard formulas. So finally, here the hedgehog of the long axis, but there is also this twist of this quantum phase-like, and they have different energy contributions to get the two very large contribution of electromagnetism and tiny contribution for quantum phase evolution. So we can see that having the electromagnetic field, they are believed not to be fundamental. It is usually said, especially due to Aharonov-Bohm effect, that there is deeper A field. Yeah, so here we say that there is even deeper field. Here, for example, M field, that its connection derivative is the A field, its curvature is the F tensor, AB fields. Yeah, so we say that there's even deeper field to make that the Gauss law counts topological charge, to build in charge quantization. Yeah, so if we don't do it, our Gauss law can return real charge, while in nature it's integer number. So for charge quantization, we get even deeper, getting this unified quantum phase, which combines electromagnetism with quantized electric charge with quantum phase 2π, which is rotated by 2π. Yeah, so we can unify them into one, this extended quantum phase, S3. And then finally we get to 4D, adding also space axis for gravity. So here is the Lagrangian once again. So yes, also we have this F mini. So Coulomb model, and there is the Landau-de Gennes like potential, which prefers some shape of molecule. So the M field is like here. It is some rotation times diagonal, which is preferred shape of our molecule. So the Higgs potential prefers some shape, and this shape has this one corresponds to electromagnetism, delta corresponds to quantum phase, G corresponds to, it's much larger, corresponds to gravity. And so here is the F tensor. If you calculate this F tensor, it looks like this. So we can see that the spatial coordinates have, here is electromagnetism, here is the quantum mechanics, here is the gravity from Bose, but then are also these terms, which we turn out to have negative contribution. So in Skyrmę, Hamiltonian needs some negative curvature squared contribution, so they will be crucial, I mentioned in a moment, to the clock propulsion I have mentioned, yeah, and also gravitational mass. So I talk about it now. to finally get electron clock like this, preferred energetically in the resting, for a resting particle. Yeah, so let's talk about the clock for a moment. So here is some recent archive about this toy model for the clock propulsion mechanism. Yes, so we have then the FIFOR model. So this is standard model of this one-dimensional, like sine Gordon-like model with this, let's say, this Hamiltonian 1/2, and here we add this kind of term. So it is Lorentz invariant term, this curvature square term as we get, but with negative contribution. So it's crucial. So if you add this term now, so phi is the kind of the structure of our particle. So now we can see that there is this phi1, that means spatial derivative of phi times temporal derivative of psi. So if there is something happening in the particle, so this is non-negative, there is a tendency, energetic tendency to also make non-zero temporal derivative of the phase. Yeah, so the field wants to rotate in the presence of some structure of particle. Yeah, so literally it brings tendency for this quantum phase evolution, psi, this coupled field, in the presence of particle. So finally we get this kind of behavior so here is standard king. So now literally some non-zero gamma is preferred as the behavior of this king, thanks to this kind of term. Yeah, so this term allows to make that resting particle already has preference for some periodic process. So becomes time crystal so this is time model, and now the full model. So let me briefly talk about the full model. So here is the Lagrange I'm considering, and going to Hamiltonian. So while for electromagnetism, going from Lagrange to Hamiltonian, we get only positive contributions. It had only two indexes, F mini, F mini. However, using 4 indexes, because curvature has finally 4 indexes, if we go to Hamiltonian, we get also negative contributions. Yeah, so the Hamiltonian gets both positive contributions, yes, the red one here, but also negative. So we get them negative curvature square contribution. So like here, this contribution gives tendency for the field rotation in presence of particle from non-zero spatial derivative. So this term is finally this term which appears here. No, it seems crucial for this electron clock. For neutrino it's more complicated, but so what you can see here. So here is temporal derivative of the twist. Gamma 1 is this twist, this quantum phase. In presence of gamma tilde is the boost. So this term makes it prefer to have both the field rotation and local boost. So local boosts are also crucial for the gravitational mass. Yes, for why charge we get quantized from charge quantization. This term also allows to give preference for gravitational mass. Yes, so here these two preferences are combined. Okay, so now let's go. So I mentioned that why non-negative charges in physics. So here we have this Haley-Bolt theorem. Yes, why leptons need to also have magnetic dipole moment. So here, because we use this field of 3 different axes. Yeah, so you have the hedgehog of one axis, and it requires some conflict here. So here is a conflict. Yeah, so here is very subtle conflict. Which we allows we require magnetic dipole moment of also for electron and for other particles. So we have now 3 different axes. There is Higgs potential prefers the shape of this molecule, and so here is the hedgehog, which requires also this magnetic dipole, and here are the QCD flux tube, which with quarks. Yeah, so here is the fractional charge. By pi would be elementary charge. Here is a fractional charge. So we can get the 2 quarks as excitation of quark string topological vortex, which finally should have this potential, which is locally is Coulomb, but asymptotically is linear. Okay, so how to get the other particles? Yeah, so this string hadronization seems very promising way to do it, because they assume that in LHC collisions they create this string and it finally decays into particles. Yeah, so we just need to find a correspondence between what they see in LHC collisions and what topological vortex can decay into. And the simplest topological vortex can decay into are just closed loops of this topological vortex. So it would be very stable and oscillating. So three types, and so it I think it resembles neutrinos. I will give more arguments in a moment. And then the knots like here seem to resemble baryons. So let's think about knots. So here we have one topological vortex and second one around it. So what we can see is that this vortex around deforms configuration inside, and this deformation is toward this topological charge. Yeah. So the presence of this vortex around enforces Hedgehog electric charge inside. Yeah? So the baryon structure prefers some electric charge. Yeah? So proton can just enclose it into elementary charge. Neutron has still this preference, but now has to compensate it. So okay, let's say two plus third, two third, one third, one third. So now we get kind of quark structure, and also explanation why neutron is heavier, because this is costly, this enlarged structure. So I think this is very nice. So automatically we get that proton is lighter than neutron, and further properties I will talk in a moment. And finally, we could get a vortex with internal twist, like Mobius string. Yeah. So I think that just such Mobius string could be pion kaon. If for one it's pion, for two it's kaon. And if there is also some vortex inside, it would be strange baryons. So doing so, the strange baryon decay, like here, would agree. Yeah? So we have a strange baryon, it decays to less strange baryon plus pion, so by one, or plus kaon by two. Yeah, so we get the kind of really strangeness as internal twist in pions counts. So now let's go to the six quarks. Yeah. So as mentioned, we have three types of vortices along one of the three axes, and they could have these local fractional charges: one third, two third. So one two third. Why two third? Because it depends if there is a vortex around. So this vortex around literally prefers, let's say, two third charge to get agreement with quarks, and the one third are required to compensate this two third charge. Yeah, so here without vortex around it's one third, with vortex around it's two third. And we can see that why U is lighter, because it's energetically preferable to have this two third in the presence of this vortex. Yeah, so that would be the preference why the U quark is lower. And neutrinos, as mentioned, seem to agree with the just simpler loops for very stable, very light, three types, oscillations. I will talk in a moment. So now we can think about what about the two mixing matrices. So for quarks, here is for quarks, it is much more diagonal. For neutrinos, it is less diagonal. So the explanation here would be that for simple vortex, it is easy to rotate the field. While for the knots, so here is for knots, baryons as knots, it's much more difficult to rotate. Yes, so being knots make it more difficult to rotate to different flavor. Yeah. So let's think more about this argument that proton neutron would be this simple knot. So the vortex around enforces some charge inside. So proton can just enclose this vortex. Neutron has to compensate it. If asking for charge distribution inside baryons, so here are some three articles claiming that neutron has positive core, negative shell. Yeah, indeed, neutron has positive core, negative shell, and indeed here we have for neutron positive core, negative shell. So it agrees with predictions. Then we can ask about the deuteron, the simplest nucleus. So now we have two baryons, both would like to have a charge. But and now they can share this requirement of charge. Yeah, so we have plus, minus, plus. So this is electric quadrupole moment. And turns out that indeed deuteron has electric quadrupole moment. So this is very non-trivial property. And naively, if you think about proton, neutron, they shouldn't be electric quadrupole moment. So, but experimentally, and this model automatically predicts quadrupole moment. Also, that the spin magnetic dipole moment should be approximately sum of the proton and neutron. So also, so I would say that the magnetic dipole moment is toward. Okay, so now let's go to neutrino. Yes, so we can think about the beta decay. So in beta decay, we would get this neutron as this minus plus minus, and now it has to shift the charge, and now there will be this topological vortex would create this loop, this simple loop as neutrino. Yeah, so let's think about them. It should literally be created by the beta decay. Should be very light and stable because it's very light configuration. However, it could have various sizes. So maybe you could get also heavy neutrino. It's not a fixed value, but rather fixed density per length. Yeah, so maybe thinking about fixed lengths is not appropriate. So we have three neutrinos as loops from beta decay and stable oscillations. So oscillations could be by just field rotations. Yeah, so between some two configurations like here. So the question is why we have this chirality, why antineutrino? Because so generally I would say that here the gravitational mass, the boosts are the same for antiparticle and for connections then should be reversed for antiparticle. Yeah, so I would say that then yeah, so okay, so then we have the energy conservation. That could vary per length from there is mainly dominating the oscillation between muon and tau neutrino like this. So electron is very different than muon and tau. So mostly there is this twisting between the two. So about sterility. There are about sterility. There are these two basic types of experiments. So one is this LSND mini boon, in which we have excess of neutrinos from pion decay, but also there is this gallium anomaly, also reactor anomaly, which is deficiency for nucleus decay. So I don't have the answer now, but I would say that there is that think about the decay of some this kind of configurations. There is also this degree of freedom, which is more than flavor. This is U1 in the flavor, which should also affect the probability of being produced and absorbed. So I think instead of being sterile, I suspect this additional degree of freedom changes probability of emission absorption. Yeah, so because if you create some value is preferred, so also during absorption some value should be preferred. Okay, so very briefly about some beta decay, beta plus decay. So one can ask, what about CPT symmetry? There shouldn't be the same. So no, because we have nuclei. So beta plus is much more difficult. So we can think that the beta minus is is from neutron mainly. So this kind of noise and then decay. For beta plus, we have a large nucleus, which something snaps inside, and now there is this positron is being created. What about chiral symmetry breaking? So as mentioned, I think that antiparticle has the same mass, opposite gamma. So I think it could explain a few properties. The hollow nuclei, as mentioned, so I think there are asking for non-perturbative explanation, what field configuration are the mechanisms. I think the topological vortices seems the only answer. So while the baryons, the proton neutron seems a simpler knot, For nuclei, we should think about larger knots, like, and which could also have these singular nucleons in large distance, larger than of nuclear force, in stable way for hollow nuclei, but the details are very difficult. Okay, so there are more problems in this mainstream physics and baryons nuclei. So, for example, so there are some issues like charge distribution. So spin crisis. So here also some spin is in gluons, some is the quarks, some is in the angular momentum. So here indeed the gluons would be this shape of this vortex. So yes, indeed, not only quarks should contain, and especially the quarks is very low, just more like approximately 1% of mass of proton neutron. So indeed, also here this is mainly electric field energy. Then there is proton radius puzzle. So if probing with electron and muon, they get different distances. So I would agree here generally, because electron and muon here would be both these hedgehogs, but with field rotated by 90 degrees. So it should be crucial for them scattering. There is neutron lifetime puzzle. So the cold neutrons turn out to have slightly longer lifetime than the hot ones. So I would say there is some excitation of the structure. Then there is EMC effect, that the quark distribution is modified in nuclei in comparison to proton neutron. So yes, so these should deform, for example, for the deuteron, that it has get a quadrupole moment. So yes, literally, it shouldn't be fixed. It should be very change in nuclei. Then there are these nucleon forces, Hall nuclei. So yes, so if you have some vortices, then effectively they will be described by nucleon forces. Then gluon bosons, again, I think they need some non-perturbative also correspondence, so what field configurations, dynamics they should correspond to. So gluons, I think there is the activation of Higgs potential, the deformation of shape of the particle, and bosons, dynamics of this vortex, like some waves inside the vortex. So here is the summary of the particles. Okay, so about potential applications, so maybe we could think about proton decay. So here, in contrast to the Feynman model, so the proton number cannot be violated, can be violated. So as it is assumed, for example, for baryogenesis and Hawking radiation, so maybe you could actively destroy protons. So if so, it would be a ultimate energy source. So enormous energy from any matter. So for this purpose, we would have to think about the proton, for example, to swing out this charge to make it out of this knot, to destroy this shape. Yeah. So having this kind of models, we could make simulations to search for some way to destroy proton for ultimate energy source. So very briefly about some technical additions. So there is this standard Austin-Frank model. Then for single axis, then we go to Landau-de Gennes for 3 different axes by adding. So here is the original one, the kinetic term. We finally exchange with this skyrmion electromagnetic-like. The potential can be prefer some shape of the molecule, some eigenvalues of this M matrix. So here is the original one. Maybe this one you should use. Maybe some different ones. So this is a difficult question. What potential to use? Maybe try to use virality to avoid it. Okay, so here is some correspondence with the gravity-electromagnetism. So maybe let me briefly go through this slide. So the shapes, the particle, antiparticle. Then here is this uniaxial nematic as the special case. And so the contributions that they depend of the differences of the lambda. So the energy contributions are different for various. For the tilt, twist, and the gravity. Here is the universal kinematic case that saying that no longer distinguishing the twist, we indeed would get this just the simpler case as in Faber approach. So here's the Hamiltonian, the Klein-Gordon. You can get approximately Klein-Gordon. Here are some calculations which can be found on the GitHub. So for example, here is the Hedgehog configuration, and looking at the phase evolution, turns out that they lead to kind of Klein-Gordon-like equation, not exactly, but close to Klein-Gordon-like equation from Euler-Lagrange. So here you can think about parametrization of this kind of hedgehog. So effective description of some object with velocity, with direction, and being particle of antiparticle are these B-spinors in Dirac equation. Then we can use only the gravitational part, the boosts, and for example for zero electromagnetic field. So electric and magnetic field as zero. Then we get also the Maxwell equation. So for gravity-electromagnetism. Okay, so there is some Coulomb-like for gravity. So here is the clock again, and let me finish at here. So the standard model here is the Lagrangian standard model. So it is huge, kind of epicycles that when something is agreed with experiments, they added new terms. And now there are problems like this, like QCD is still mostly non-perturbative. So maybe we should find something for some deeper model for which this huge Lagrangian is effective description. Yeah, so this deeper model should be non-perturbative electromagnetic-like with charge quantization. And to get this electromagnetic light with charge quantization, we should use like this one for F being curvature for charge quantization. So in liquid crystals, you can get it. So also experimentally, it is very close. And using this simple looking Lagrangian, especially at least quantitatively, we get very good agreement with the known physics, like the unification of electromagnetics, quantum phase, and gravity. We get in charge quantization, regularization of singularities to finite energy. With three leptons, the hedgehog of one of the three axes, neutrinos of the topological vortex loop, very stable oscillating, come from beta decay. Three families of baryons as the knots with proton lighter than neutron as required, deuteron lighter than proton than neutron. Deuteron with quadrupole moment, nuclei as knots, also halon nuclei. String hadronization suggests how to assign the particles to topological defects. So finally, hopefully, the effective description of the proposed model will be in agreement with the standard model Lagrangian, but it is a lot to work with. So thank you for your attention.